Question number 9. Find the products for the following reactions.
So, these reactions are very famous reactions as it's evident from the reactants. In these questions, you have a diene, which means 2C double bond C. As in the first case, this is the diene. And secondly, you have dienophile. As the name suggests, it's a lover of diene. As in the first example, you have this one, and you have Lewis acids like Bi or AlCl3, and also you have high temperature. All these comes under the category of a famous reaction called Diels-Alder reaction. Now, let's see what this reaction is. This is a concerted reaction, which means that it proceeds in a single step. Let's look into the simple case of it, where you have a simple diene and a simple dienophile in the presence of a Lewis acid, say AlCl3, at high temperature around 200 degrees centigrade. Now, these bond shifts occurs at a very high temperature and in a concerted manner. You will get a closed ring. It's very simple for these simple cases. Now, what if you are given the complex case, like in this question? If you take, in the first case, you have the diene as so. As you can observe, bond shifts here. So, alternately, you have two possible shifts. One is either shifting in this direction or shifting in the opposite direction, that is this to this side and this to this side. Now we have to see which one of it is more favored. Now, if it is shifted in the first direction as indicated by red arrows, you are going to get this one, a positive charge here and a negative charge here, and this one a double bond here. Now, if it goes as indicated by the blue one, you will get a positive charge here and a negative charge here and a double bond here. Also observe that this is more stable. This one is more stable because this positive charge has hyperconjugation possible with this methyl group, whereas this positive charge there is no possibility for hyperconjugation. So you got to have this one. And for the diene, if you take where it is CHO, I'll write the structure for you, C double bond OH. Here also you have two possibilities for bond shifts, either in this way as indicated by blue ink or in this way as indicated by red ink. Now, if it goes through the path indicated by red ink, say, you will get a compound like this, H. Bond shifts in this direction, so you have negative charge here and a positive charge here. And if it shifts as indicated by the blue arrow, you have negative charge here and a positive charge here. Now, you have to think which of it is more stable. If you look carefully, C double bond O is strong electron withdrawing group, because in the C double bond O, the structure exists like CO minus C plus. If you have strong electron donating group, say like the first case, you have minus charge here and plus charge here, it's stabilized by forming a double bond. Whereas if you have a positive charge on it adjacent to it, O minus C plus minus, so it undergoes severe repulsion. This already is discussed previously, so I think you can understand it. So in between these two products, this one is formed and this is not formed. Now the thing left out for us is couple both the products that we have. So for the diene we have this one, and for dienophile we have this one. Let's write down these things. A positive charge here and a negative charge here, and if you take this one, that's a dienophile, you have C double bond OH here, negative charge here and a positive charge here. Now just couple these things, these charges, you're gonna get this compound. But remember, as I have done splitting here, it won't go actually in this way because it's very concerted step. It proceeds in a single step and it won't have these many steps. Now if you look into the second case, where you have diene as this and dienophile as this, I want you to try this one. I'll tell you one thing. OH here is electron donating group.
Okay.
Unlike C double bond OH, which is electron withdrawing. Now I want you to do is just shift these bonds and see which of the structures will be more stable and write the answer for it. I'll give you the answer if you want.
How about we draw out the more stable structures?
This is already, as I have explained here, if you have positive charge next to oxygen, it will donate its lone pairs.
Alright.
And it will be fulfilled by octet. It completes its octet, so it gets more stabilized.
Okay, so this is the main thing to be kept in mind while solving this question.
Yes.
Right?
Yeah.
Okay, so let's give them the answer so that they can look at it. Students, if you want to solve it on your own, we'd recommend you pause the video for a while and solve it. The solution's gonna come right after this. So let's draw out the solution.
The answer for it is methyl group here and an OH group here.
So that's the answer right in front of you. Go through the mechanism that we've suggested above and it'll be very easy for you to solve it. Alright, let's move to the next question now. Question number 10. Find the number of optically active products obtained upon reductive ozonolysis of the following compound. Now the compound looks fairly complicated, which is why we've got to be very careful as to how we find the result to this, and we've got to be very careful at each and every step that we do it. So let's get this started, Gopi.
Yes. First, before solving this, as I told you in the theory, now I'll discuss ozonolysis in detail. First, consider an alkene, say this one. Now in the ozonolysis, first thing you add ozone in the presence of non-polar solvents like CCl4 or N-hexane. Now it undergoes a very complicated mechanism and finally it will give you an unstable ozonide, which is, I'll show you that. This is ozonide. It's very unstable because of presence of O-O bond, and you know that O has two lone pair of electrons, and these two lone pair of electrons repel, and as a result of it, it will be very unstable. Now in the ozonolysis, next I told we have two parts. One is reductive ozonolysis and the other is oxidative ozonolysis.
Okay.
As I have told you, this ozonide is very unstable, so what happens is it cleaves away in this way, and you will get a carbonyl compound, and also nascent oxygen. Now let's talk about this reductive ozonolysis. In this we use reducing agents like zinc, Me2S, PH3P. As I have told you, these are reducing agents. Now they take up this nascent oxygen and zinc gets converted to ZnO, and similarly this will get converted into S double bond O, which is dimethyl sulfoxide, and this one to P double bond O, PH, PH, PH. So in reductive ozonolysis we say that since we are adding reducing agents, they take up the nascent oxygen and they get oxidized. Now if we take oxidative ozonolysis, we use H2O2, which is an oxidizing agent. Now it too gives H2O plus nascent oxygen. So this will give nascent oxygen, and we also have nascent oxygen. So this nascent oxygen will act upon the hydrogens of C double bond C, and they get them converted to COH. For example, if you have CH3 H H H, let's say, if you subject it to reductive ozonolysis, you will get C double bond O H H, and here also C double bond O, CH3 and H here. If you subject it to oxidative ozonolysis, you will get C double bond O, OH, OH, and C double bond O, CH3, OH. Now this is very unstable because two hydroxyl groups on same carbon, they undergo repulsion. As I have told you previously, they have two lone pair of electrons and they'll repel each other. So it dehydrates, it converts to CO2.
Okay, and CO2 is a very, very stable compound.
Yeah, it leaves away.
Okay.
Now let's come back to our question. I'll redraw the compound for you. You have H here, a double bond here, C here, ET here, and to this another methyl group is attached, and ET, a double bond here, C, a methyl group, hydrogen to it, Cl, Me, C double bond C, H, CH3. Now you have subjected this to reductive ozonolysis. So what you do is just you break down these bonds, and you need not change these hydrogens because they won't get converted to OH. Break down these bonds and add double bond to each of them. So you will have H double bond O and O double bond C, ET here, and methyl group here, and C, ET here, and C double bond O. Now this is one compound, and you also have one more compound like for this thing. For this thing you have O double bond C, C, Me, H, C, Cl, Me, C double bond O, and O double bond C, H, CH3. Now, in the question you are asked to find out number of optically active products. Now, these are our final products. So, to find the optical activity of it, you need to check for the chiral carbon and see if it has a non-superimposable mirror image. First, look for the chiral carbon in the given product, in the obtained products. Now, the first one, if you take, it has no chiral carbon, and the second one, if you take, is it has one chiral carbon, and the third one, if you take, it has two chiral carbons, and the fourth one has zero chiral carbon. Now, please make sure that for this carbon, ET and Me groups have fixed stereochemistry. So, in other words, we can say that this compound is optically pure. So that is, there won't exist an enantiomer for it because these ET and Me groups are already fixed in their location. For example, if you are given like this, then it shows that these are not fixed in its location and they can be changed. So there can be enantiomer possible for it.
Okay.
So from this compound, instead of two, only one compound is formed. Now come back to this compound. You have two chiral carbons, and if you take this one, its stereo is not fixed. As you can see, you have given just dashes for Me and H, so they can exist R and S configuration for this one. As a result of it, two structures are possible from this carbon. But if you take this carbon, its stereo is already fixed. That is, Cl group and Me group attached to this carbon have a fixed stereochemistry, so it's optically pure, and either R or S are formed here. So final compounds are one from this one and two from this compound. So on the whole, we will get three optically active products. The interesting thing is that it's a previous IT question and it has been already asked in 2010.
Alright, so now that you've seen that this is a very tricky question, you can go over it again and realize at what places can we have an R and S configuration and at which places can we not.
Yeah.
And that's pretty much all that you need to know to be able to solve this question.
Generally what students do is, for this compound, without looking at it, they'll write two products from this and they'll write 2 into 2 products from this compound. So they'll end up getting 6 products. But if you observe, the trick lies in this one. The stereo of these things are fixed.
Exactly. So we should be very careful when approaching such problems, and JE has been known to be very clever with these kind of problems. So let's move on to the next one now.
Yeah.